Okay, so it's time to 2 p.m. So let's start the stage 1 in the afternoon. I'm the chairman of the jury. So before the competition, let me introduce our jury. My name is Su Jiongwu from Jiayi University. The second jury is from Donghai University, Lin Zhongxin 教授. The third one is Gan Hongzhi 教授 from 中正大学. The fourth one, 曹俊华老师是 from 中正大学系. The last one is 江普俊老师是师范大学护理系. Let's welcome. So before we start this competition, every team to introduce every team's names. So please from Feng Xinhai, Captain. So please introduce.
Hi everyone, I'm a captain from the team C1J, and my name is Chen Yujing. This is Lin Hengzhen, Liu Yuchen, Wu Weizhong, Zheng Guowei, and we are from 14th Senior High School.
Okay, let's welcome. So the opponents from Pingdong Senior High School, Captain, please.
So I'm the captain from Pingdong High School. This is Lin Nairo, and this is Zhang Yihao, this is Hu Junhao, this is Liu Weicheng, and this is Wang Jianhong.
Okay, thank you. So the reviewer from Jincheng Senior High, please.
I'm the captain from Jincheng High School Team Scientist, and Mark, this is Ollie, and Jen, and Jennifer, and Julie. Thank you.
Okay. So let's start the first part of the opponent have to challenge the reporter. Please.
We'd like to challenge number 9, oscillating through.
We accept it.
Step. Okay, so the reporter accepts the problem number 9. So it's time for preparation of the reporter. We have 5 minutes. So this time, please write down the reporter opponent and reviewer's name on the blackboard. Please. Okay, so the presentation of the reporter, you can start.
Okay, onward juries and fellow competitors. This is the reporter from Team CYJ. My name is Brian Hu, and today I'm gonna present the problem number 9, oscillating screw. So first, it's a problem statement. When placed on its side on the ramp and released, the screw may experience growing oscillations as it travels down the ramp. Investigate how the motion of the screw, as well as the growth of these oscillations, depend on the relevant parameters. So there are two main focuses. First, why there are growing oscillations. The second, how do relevant parameters affect the oscillations. So first is the observation. So that we can see that when the angular velocity are the same, the tangential velocity is proportional to the radius. So that causes that the velocity 1 is larger than the velocity 2. So now we can know that the difference of tangential velocity causes the oscillation. Now it's the observation. We would like to separate the observation to 4 parts. The first part is that it will oscillate with a little descent. The next part is that the oscillation didn't grow along the descent, as you can see in the graph. The third part is that oscillation grow with the descent. And the fourth part is that it will start to spin, as is shown in the video. So now I would like to talk about the ideal model. So, the actual screw is hard to calculate. So we can separate this into 2 parts: the rod and a hat. So, and each other has a separate radius and a length. Now we define it. So the density will look like this, and the volume we can separate it from the volume of the head and the volume of the rod. And the mass, we can add these two together, the mass of the rod and mass of the head together, and we can get the total mass of the screw. So now into the first analysis. And there are, because we need to analyze the force that affects the whole motion. So there are the mg sine theta that caused by the gravity, and there are the friction and different friction, the friction of the tip of the the friction of the tip of the screw and the friction of the head of the screw, and the direction of the friction will always be opposite to the direction of the sliding velocity. And there are, because there are contact points, so there have the normal forces on the tips and on the head. So with this force analysis, we can now get the degree of freedom. It's the position x, y, and the angle theta z and theta 1. So now we can talk about the moment of inertia. So now we view the screw as kind of a cylinder. So now we can know the cylinder's moment of inertia would look like this. And then we would analyze the moment of inertia for the y-axis. It would be like this. And because of the rod, radius of the rod cannot be ignored, so we have to analyze the moment of inertia of the rod. And it would look like this. And so now we can analyze the moment of inertia for the z-axis. This part is because that we now consider a rod as a cylinder. So now we added this part of the inertia of the rod. So now the moment of inertia for the z-axis would look like this. Now we're going to talk about the normal forces. As previously mentioned in the force analysis, there would be normal forces in the actual. The normal forces would actually affect the motion. So now we can describe it at this. And the DCM I want to talk about is the distance between the pivot and the center of mass. The pivot, we would put that as a contact point between the tip of the screw and the ramp. And now we're going to talk about the friction. So the friction, because of the sliding motion, so we would take this friction as the kinetic friction. So the displacement we're gonna talk about the displacement. The displacement of the tip of the screw and the screw are different because of the extra tangential velocity caused by the rotation. So it would be different. And now we can get the equation of motion by Newton's second law. There will be two equations because there are two positions, as I mentioned in the previous presentation, the x and the y. And now we can talk about the equation of motion that's rolling around the z-axis. We could get the EOM like this, and this is the frictional torque of the equation of motion. And the one axis, and the screw that rolling around one axis is gonna look like this. Now we can talk about energy transport. This is energy side. So the gravitational potential energy will be transformed into the rotation energy and the energy decay caused by friction. And we can see that there is a displacement here. So the total path, but the total path cannot be predicted. So we can solve the motion numerically with Python. And we can also analyze the growing oscillation because what caused the growing oscillation? The gravitational potential energy would be larger than the total energy decay caused by friction. So that causes the actual growing oscillation. And decaying oscillation is opposite to the growing oscillation. The gravitational potential energy is smaller than total energy decay caused by friction. So now we can know that how these are made. Now, we use this Python to calculate the equation of motion. And we now compare the experiment to a theory. So we put the inclined angle as a 3 degree, and we compare it to the theory part. And that we use Python to write it down. The theory part, when we compare it to the actual experiment, it would be matching, whether it's decaying or growing. Now we can talk about the parameters. The ramp's angle and the length. First, the ramp's angle and the length of the screw. And now, third, the radius of the head of the screw and different surface. First, we're going to talk about the ramp's angle. With the help of a protractor, we can change the angle of the ramp, like this. Next, we talk about the radius of the head. The radius of the head from right to left is 4 millimeter to 5 millimeter. And this is the experimented setup. We use this book to support the ramp and the protractor to change the inclined angle. And so now we're going to talk about the measurement. So we use this octangent slope times slope to get the delta z. And we use this formula to get the friction coefficient. So this is experiment 1. We change this ramp's angle. We use the 22 millimeter length, 5 millimeter head, and wooden board, and change the angle of the ramp, and measure the different types of oscillations. So now we can separate it into 3 parts: the decaying oscillation and growing oscillation, and the screw that started to spin. And it would look like the video. We can use this formula to explain the theory, explain the experiment. Sorry. And so this is the gravitational torque and the frictional torque. So when the inclined angle increases, the potential energy increases. So it causes the oscillation. Now we go into experiment 2. The screws there. We use the 22 millimeter length, 5 millimeter head, and 16 degrees inclined angle, and the wooden board, which have the friction coefficient of 0.358 to change the length of the screw and measure the different types of oscillations. So now we can separate it into 2 parts: decaying oscillations and growing oscillations. We can use the moment of inertia to explain the theory. So when the length increases, as it writes here and here, the moment of inertia around the z-axis also increases. So we can use this formula to explain the torque, the tau is the torque provided by gravity. It's constant. And when the theta z is decaying, and so the moment of inertia would grows. So this is experiment 3, different radius. We use this 22 millimeter length wooden board and 20 degrees inclined angle and change the radius of the head. Measure the different types of oscillations. And there are 2 different types of head. And the small one is 4 millimeter radius is 4 millimeters, and the big one is 5 millimeter radius. So we can also use this equation to explain the theory. Because the radius is proportional to the tau 1, so when the tau 1 grows, the radius grows. Now we turn to the experiment for a different frictional coefficient. We use the 22 millimeter length and 20 degree inclined angle, 5 millimeter head to change the surface of the ground. Measure the different types of oscillation. And now we can get, there are 3 different types of coefficient, friction coefficient. And we can also use this formula to explain it. And now we get to the conclusion. We can separate it into 4 parts. The increase of the inclined angle, the increase of the length of the screw, different radius of the head, and different friction coefficient. So now, this is the first part, the increase of the inclined angle. When theta z's amplitude grows over time, the oscillation grows. The increase of the length of the screw, when the tau stays the same, and the IZ increases, so the theta z also increases. Different radius of the head. When the R increases, tau 1 increases. The different friction coefficient. The theta z's amplitude decreases over time, so the oscillation decreases. So, thanks for listening.
Okay, so it's time to the from opponent to question to the review. Opponent.
Alright, I heard you just mentioned the Ram's angle.
Yes.
Can you explain that more clearly?
So Ram's angle is just equals to inclined angle. Yeah. So the inclined angle means that we changes the that we mentioned in our experiment setup. We use this protractor to changes the inclined angle.
How many angles have you observed?
Oh, so we observe which here we use these angles 3, 14, 15, 16, and 18 because when it's
Okay.
lower than
And you have changed the length of the screw.
Yeah.
And if the length of screw gets longer, will the mass get larger?
yes, but it's not. It's ignorable. And in our results, and yeah,
It
it's
would
shown here.
influence the result.
It would not in our result, but in the theory it would. In fact, that affect a small bit.
Okay.
Okay.
And you have used different materials of the surface of the ramp.
Yeah.
And how many different materials? Right?
3. It's shown here. Different friction coefficient. There are 0.385 and 0.708 and 0.71.
Oh.
0.
And
Yeah. So yeah.
okay, just it.
Okay. So it's time for preparation. Okay, your time. Opponent take the floor. Your time is 4 minutes. And later discussion, please intend.
Okay. And this is scenario, and we're going to appear observation of the number 9 oscillating screw. And then here's the problem statement. It says when placed on its side on a ramp and released, the screw may experience growing oscillation as it travels down the ramp. And they investigate how the motion of the screw, as well as the growth of this oscillation, depend on the relevant parameters. And here's the structure of solving the problem. They first shows our phenomenon, and then they use several theories to explain to us how the friction is into this experiment, and then they use the experiment to prove that the theory is true. As for part of the report, they have theoretical model via literature, and they have a simple, understandable, qualitative explanation of the phenomenon, and they have appropriate use of media. They use videos and graphs to show us the experiments, which makes me understand more about the experiment. I have an explanation of connection between density and experiment. As I remember, they show a density, but they did not explain it. And they have incomplete investigation of different mass, and they late explanation of the grade. As for experiment, they have accurate and they are accurate and reproducible, and have sufficient investigation of different parameters, and they have comparison of different variables. However, they have some test of randomness. They have no measurement of the height, and they need investigation of the track. And for the theory part, they have relevant modeling of the theory, and I can understand most of them, which is a clear explanation. And they have well understanding of the formula, so they can complete the chart, and they can get data. However, they are unclear how modification of the theory was actually done, and they have insufficient explanation of the center of the mass, which is the true center of mass. I think this is worth discussing later. And so later, I want to discuss with the reporter about the center of mass of the screw, and the different friction, and the phenomenon of oscillation. Although his explanation is quite clear, I still want to know more about this part. And this is the end. Thank you.
So it's time for discussion.
Okay. We just mentioned that the length of the screw,
Yeah.
and the mass will also change.
Yeah. Yes, but in this experiment result, we think that the biggest change in the length is about that it will change the here.
What do you mean?
It will change the angle right here. So the
I mean the screw, not the angle.
I mean the parameter. Okay, so can you repeat your question?
Wait. I want to tell you my opinion first.
Okay.
And if the mass gets larger, the mass of center would also be different.
Yes.
So perhaps
Okay.
the oscillation would also be different.
Yes.
This is my opinion.
Okay.
Now?
Yeah, and so the center of mass will change, right? But I think center of mass is not like the most relevant to the experiment. So we didn't did that comparison. Yeah, but yeah, I think you're right on so.
Okay. And Just tell us that it's mostly influenced by the friction of the surface.
Yes. No. Do you mean the cause of the oscillation, or the? Do you mean the cause of the oscillation?
Yeah.
So I did mention in the first part that I think it's the difference of tangential velocity causes the acceleration, and the difference of tangential velocity can be caused by different factors, including normal factors, normal forces, center of mass, like you mentioned, and friction. Yes. So this is the cause of the oscillation.
And as it gets down, was the velocity of it get faster or slower?
You mean
The screw.
the screw's velocity? The velocity would be get. What velocity do you mean? Do you mean the falling velocity?
Yeah.
Yes, it would get bigger because of the gravity.
Because of the gravity.
Yes,
Okay.
because when it falls down, like when it falls down, the gravity would have a acceleration, so it would get the velocity would get bigger, right?
Oh.
Yeah.
Which
So are you asking?
Which means the friction coefficient does not influence the result so much because it gets faster, and it is mostly influenced by gravity. When it comes to the velocity of the falling.
But velocity of the falling will not influence the result. Motion.
Have you any track of the oscillation of its acceleration?
Yes, this is the track of the oscillation. This is a track. This is a graph of the oscillation. It's so the x-axis is the so the x-axis is the movement, the oscillations right there. Yeah.
So you just move straight down, or you will get to the other side.
What do you mean get to the other side?
I can use the force.
Oh yeah. You can use it.
This is your run, and you let it down here,
Yes.
and will it just go down, or
I think it would be like this.
what?
Oh, you mean the oscillations or the screw?
The track.
So you mean the total of the screw, the center of mass of the screw would fall like, it would depend on the friction. So if it would be falling down like this, in the most part of the experiment that I did, but it would have the situation like this also.
Okay, so it is mostly dependent by the friction of the surface.
I wouldn't say that, but then maybe.
Okay. And if you use different, if you take the variable. And your reliable has several discussion about this phenomenon.
Yes.
Will it influence its oscillation? If it is faster or slower?
What do you mean?
So just like this, and if the friction is smaller or the height you put it down is.
Also, that will depend on the incline angle, which is the ramp. So the height you mean is the incline angle. So I will use the board here. So this is the incline angle. So do you mean the height here?
Yeah.
So it would. So the height here also equals to the incline angle. So we change the incline angle like this. The is, and this is L1, L2. So if theta's bigger than phi, then L1 will be bigger than L2. Yeah. So that's the height right there. You mean that?
If you just use it, have you put it there and put it there, just different height?
I think it would be different parameters. So you mean different part of the ramp?
Yeah, right.
So like starting right here and starting right here would get the same result. But because of the like lack of the lack of like
The distance to
yeah,
start oscillation.
yeah.
Oh, so it needs a distance to start the oscillation.
And we can observe it better. So that's why I started from the top of the graph.
Oh, okay. So how long is the distance?
1 meter. So the top of the ramp and this is 1 meter.
Well, the
So-
length
so-
for
so-
it to start oscillate.
Also, it depends on the incline angle.
Oh, okay.
But we didn't calculate that. So, and we think that it's not relevant to the compensation.
Okay. And let me see the radius. The radius of the head of screw.
So here. So this is the sorry. This is the formula mirror and this is the height mirror. Yeah.
Okay, explain it more.
Also, so the radius of the head is the radius from this part. Like, it's just the radius of the head of the screw. If we use this, yeah, it would be the radius. It would be like this. Here is the radius. But
I know. Yeah.
Yeah.
So you use. Oh, so.
So there are two different radius of the head in my experiment.
And you use that to start your experiment, but it's just like a photo.
What do you mean, like start the experiment?
The previous photo you just shown me.
Oh, sorry. I will give it there. Yeah, this.
You use this to start to do your experiment.
Yeah. So two different radius of the masses. So the radius of the masses would change the angle gamma here. So we think so the radius of the head would change. The most relevant part is the gamma. It would change the gamma, and it would.
And the volume attached to the surface would also be different.
What do you mean, like different? The surface we use in the experiment are the same because we only change one parameter at a time.
The surface that is on the surface.
The surface that is on the surface.
Yes.
And can you explain this more clearly? Like this. Yeah. It would be all the same because that it's the same type of screw, just with the different radius of it. It would be the same type and the same material.
But this and this are not the same material. And you just put a ball here.
No, we don't. We didn't pull the ball there. We just changed the different screw.
Oh,
We changed the screw.
Oh, okay.
Yeah.
Oh, okay. So the soil friction does not change.
So the friction wouldn't change yet.
Okay, and the last question, why would it oscillate? Why would it oscillate?
So it was mentioned in the observation part. So this, when the angular velocity are the same, the tangential velocity.
Oh, I
Yeah.
understand it.
Yeah.
Okay. Thank you. Thank you.
Okay. So, Bonnet, you have to summarize.
In the previous 10 minutes, we discussed about several things. First, we talked about the center of mass, and if the length of the screw is longer, and perhaps the center of mass is larger, and I did not discuss it. I thought it's a parameter that worth discussing. And they also told me that the height, they need a certain length to start for the screw to start to oscillate. I think they should mention this on their report more, so that I can understand more about this experiment. And the rest, I think he understands quite well about experiment. That's it.
Okay. So now it's time to review, question to review to the reporter in your opponent.
Okay, so thanks for a reporter and the opponent's discussion. So the first question I want to ask the reporter about is, do you think what conditions does the separates the oscillation from growth to like decay the oscillation? What can you define a boundary value that?
Yes, we can define, we did mention it right here. So 15 to 16 degrees is the critical angle to ground decay.
I see. And how do the opponent think? Is there a boundary value that can describe it?
I think this is a quite interesting question, but at this part, I think I will agree with the reporter.
Okay, thank you. So next question about, do you think what kind of decay mode of the oscillation in your page 21?
Yeah.
Yes. How do you think the decay, the total energy decay? What's the mode? Like exponential or it's like linear decay?
It's exponential decay.
Exponential. And may I ask why?
Because we we use this graph to.
Okay. Okay, I got it. And how do opponent think?
With the results of the reporter, I think I can answer this question quite well, but I think his thought is similar to mine.
So you both think that it's exponential decay?
Yeah.
Okay, so the next question I'm going to ask both of you about is, what kind of friction in the motion do you think is used, like kinetic or static?
Also, I did mention that in this friction part, so I considered it as a kinetic energy.
And how about the opponent?
Since it has acceleration, so my answer will be the same as the reporter.
Okay, so next question I'm going to ask is about that. So do you have the calculation of the period? Do you have considered calculation of period?
Period. Do you mean that? Oh, do you mean the period like this?
Yeah.
So we didn't calculate that, but we
So
can. In a
then,
future.
do you think that it's a fixed value, that it's a constant value? Or
No,
is
we
that-
don't think it's not a constant value
Yeah.
because it decays and
Okay.
grows.
Thanks. And how the opponent think?
And this is a quite interesting question, so mine will be the same as the reporter. I will agree with the reporter.
Okay, so both of them think it's not a fixed value. So here's all of my questions. Thank you.
It's time for preparation of the review.
Okay.
Okay, reviewer, take the floor.
So, honorable jurors and fellow competitors, I'm a reviewer from Team Scientist, Jingshan High School, and today I'm going to review problem number 9, oscillating screw. So here is the summary of the report. That the reporter helped us understanding the problem which has the growing of oscillation, and also they show us the tangential gravitational velocity. And in a theoretical analysis, the reporter do the force analysis, moment of inertia calculation, and also the normal forces calculation and the frictions calculation. And secondly, you consider a rod as a cylinder and had head on it. And the third part is the equation of motion, and they have also considered energy transformation. And in the experimental confirmation that they have simulation based on their equation of motion. And they do some parameters like the ramp angle, screw stance, radius, and friction coefficient. And about the reporter's performance that have good merits is that they have clear picture and definition in the coefficient. And also they have clear graph which can explain the phenomenon. And the third part is they have adequate experiment data that can show us for the experimental results. And the possible next steps, that the first one is lack of explanation in amplitude decay, and the second is quantitative conclusion and the lack of calculation of period and the decay analysis. And the summary of the opposition is that they have discussed about the center of mass and different friction and also the phenomenon of the oscillation. And here's the opponent's performance, that their good points is that they point out the missed points by a reporter, and they helped us to understand the motion of the screw. And the possible next steps will be that their lack of understanding about theory, so they asked a lot about the theory parts, and about the discussion that the opponent asked about the phenomenon of the oscillation, that the mass and the effects of the mass on the oscillation will be different, and the reporter response is that the difference of tangential velocity will cause the oscillation, and in our reviewer's view that we agree with the opponent. And in the next discussion, which is the center of mass, and the points raised by the opponent is that they think the mass will change, so the moment of inertia will change as well. And the reporter's response is that it's not the most important part in this phenomenon, and we agree with the opponent that we still need to consider some about this. And the next is about the reviewer's questions, that we asked about the decay model and the total energy decay. That the reporter answered us as the exponential decay, and the opponent thinks that it's also the exponential decay. But in our reviewer's view, that we think it's because the decay is caused most by the friction, so it might be linear decay. So next question is the static friction or kinetic friction on the phenomenon. The reporter and the opponent both think it's the kinetic friction, and the reviewer think that they might contain static friction because it is the rolling motion of the screw as view. And the next question is the calculation of period, that the reporter doesn't calculate, then opponent thinks the same as the reporter, that the period will change during the experiments, and we agree with the reporter that the period will change during the experiments. And in our general suggestions, that is that maybe the reporter can calculate the period and also the amplitude decay of the oscillation decay fits in linear or exponential, like to prove their experimental results. Thank you.
Okay. So final concluding remarks. Reporter, please.
Okay, so this is my concluding remark. So first, I will talk about my experiment. So the setup is bricks to support and protractor to change the incline angle and the ramps. And the parameters are ramps angle, screws length, different radius, and different friction coefficient. So the main discussion point is about parameters. So first, the opponent says that if we change the length of the screw, it will change the mass and also change the center of mass. And this part, the reporter agrees with the opponent that we should not change the mass and change one parameter at a time. And because of motion, So the cause of motion in the report, in my opinion, is that the different tangential velocity causes the oscillation. So the friction and the friction or normal forces or some other forces are just the helping of the differentiate the tangential velocity. So the fixing part is that maybe we can add more parameter like the mass to or changing the different material that can change the mass so that we can get more experimental results and we can compare it more. So thanks.
Okay, so it's time for our juries to ask all of you. So please, any question about our jury? Please.
The reporter, can you show me the video? I think it's on page 5.
Okay. Sorry. Page 5.
Page 5 is the video.
Page 5. So, yeah.
Okay, what I want to ask is, for right this moment, so the oscillation is slowing down, right?
Yeah.
I want to ask, what is the real component? Is there a friction here? Or if there's a friction, the friction is kinetic or static? At the
So-
last point. Okay.
So me first. So we think that it's kinetic friction. There is friction, and it's the friction of the direction of the friction is always opposite to the direction of the sliding velocity. And so the friction, we think that is kinetic energy because it's always it's moving. Yeah.
Okay. How about do you understand my
Oh,
Okay.
I think it's the static friction because it just gets lower and lower.
In my reviewers view, that we think they might be contain this static friction and kinetic friction because there is a rolling, which is the static friction, but this is sliding of
No, just the last part.
just the last
Okay.
part.
As you see, the
static.
static is fixed. Okay. The static.
We think it's static
So,
because of the rolling
so you
motion.
think the oscillation is linear. So the friction is constant or not?
The friction might be constant because it's
If
static.
it's steady friction,
Yeah.
then it's constant.
Well, in the rolling situation, that contact point change each time, so it's not keep moving on the plane. The contact point changes during time, so I think it's constant.
About this, your opinion or
So I did not agree because it would not contain static friction and kinetic friction at the same time. It wouldn't be when there are any movement here. There will not be any static friction when there's any movement here. Yeah. So it's in my opinion, it's kinetic friction.
Okay, any more questions?
Good question. So, the problem I ask you is the screw sliding as well as rotating. So
Yeah,
it looks to me,
yeah.
for this particular one, it's not sliding anymore. So my question is, in your investigation, is whenever it stops sliding, then the oscillation decays. But if it continues to slide, then your oscillation increase. Is
No,
that
because there are
understand?
sorry. Okay, you can finish it.
You show every time you change, there will be decay and increase
Yeah.
in the rotation. So my question will be, is it coincident with the sliding motion?
No,
For
because
this particular one, the other one, then the screw stop sliding and it decays. So my question is correlated in your experiment?
so the sliding motion is not correlated to decaying or growing, because
This one is growing and sliding.
yeah, so this part it's not growing, it's decaying while sliding, and this one is growing while sliding. So it's not correlated to the yeah. So it's my opinion. So sliding motion is not related to the growing or
Okay, so my question is to the other opponents and the reviewer. If the screw stop sliding, is that part of the question we should investigate? When the screw stops sliding, is that part of the phenomena we should investigate?
In reviewer's opinion, that we think is when it stops sliding, it will be more like a pendulum motion, and which is a very interesting phenomenon. That's not the most points that the problem asks us, but maybe we can investigate it. But we don't think
it is or it is not.
it's not.
I think it's not part of the question.
Okay. No more questions. So it's time for our jury. Scoring time. Okay, so already? Yes, okay. So I do 6, 9, 7, 6, and 6. The second opponent. Okay. Please. 5, 6, 7, 6, and 6. Okay, the final for the viewer. Please. 6, 8, 7, 7, and 8. Okay. Okay, so I announced this stage is finished, so captain can be interact with this for the second round. So now I announced reporters from the team Myro, opponent is from the side iron test. So the reviewer is the CYA. So now it's time for the opponent have to challenge to the reporter. Please.
We would like to challenge problem number 8, OS pendulum.
Challenge accepted.
Okay. So problem, change, problem 8, set. So it's time for the preparation. So now, write down each team of the lab on the paper. Okay, so reporter presentation.
This is Chimero, and we're going to record question number 8, Euler's pendulum. And here's the problem statement. It says that take a stick plate of non-magnetic material and fix a neodymium magnet on top of it. And suspend a magnetic rod, and it's also said which can be assembled from cylindrical neodymium magnets and underneath it. So we're going to deflect the rod so it touches the plate only with highest H and we release it. And we're going to study the motion of such a pendulum under various conditions. And this is our video, as you can see. And we're going to main focus is how different pendulums work and how different variation influences the movement of the pendulum. Here's our phenomenal observation. And this part, this is our Euler's pendulum. And this is the track of it. As you can see, there are many different ovals, which is less irregular than the one on the right-hand side. And this is a single pendulum, and as we can see, the track of it is more regular than that of Euler's pendulum. And we're going to say that it has quite similarity between Euler pendulum and the Y pendulum. And we first take a look at the Y pendulum, since if we observe it from the bottom of it, and we can say that the movement on the t-axis is this, and the L is for this, so so actually what is actually moving is just this part. However, as for that on the y-axis, the whole line is moving. So there are two reasons. First, Ty is larger than Tx. So each time the pendulum swings, you have a deviation. And the second is that the height of the center of mass is changing at each second. So it will also influence the period of it. And next, let's talk about the Euler's pendulum. For the whole F equals minus mg sine theta plus fb, and fx equals m and g, and with the mass and the g is the gravity. And we also discussed several things, the friction between the surface and the magnetic pendulum. However, since the magnetic pendulum surface that touch the table is different at each second, so we'll not take it in consideration. And the magnetic field is not uniform. Each spot of the magnetic field is not uniform, so we still won't take it in consideration. And in the general case of two-dimensional oscillation, the angular frequencies for the motion in the x-axis and the y-axis directions need to be equal. So the equation becomes like this. And I gotta say that two-dimensional harmonic oscillation motion for various phase angles equals delta equals alpha minus beta. So in this picture we can see these are the angles of the pendulum. So if they are the same, that would be close to this picture. And according to my experiment, the two main forces that influence the Euler's pendulum is not the same, and their angles are not the same. So it would be right close to this one. And here let's discuss about the Lorentz force. Since, as you can see, my experimental schematic diagram of my experiment is like this. So we can see it as a magnet. We can see that there is a magnetic field, and the Lorentz, of course, in my experiment, the the angle doesn't 90 degrees, but an Lorentz force it would take the axis. This is how the y-axis moves. So, and how about the okay, I think I'll talk about it later. And here, let's see our variation. Variation 1 is the magnetic number of the pendulum. And at this part, there are just 1 magnet above the pendulum, and there are 50 magnets under of the pendulum. And this is its track, and this is y-axis track, and this is y-axis track. And the main force that influence that of the x side is the gravity, and the one that influence the movement of the y-axis is the Lorentz force. And how? We'll discuss about that later. Let's see other charts first. And at this part, there are just 40 magnets, and we can see that the oscillation is not so obvious as the next one. And here it is a 30. As you can see, that the track is even more close to each other, and at this part we can say that the x-axis doesn't move so much, and what moves more is the y-axis. And this is the 12 magnets of the pendulum. And there are just 11 magnets. We can see that it's just really close to a line. But the movement on the y-axis is still moving on. So here's our operation. With more magnets beneath the pendulum, the time tends to take longer. And with more magnets beneath the pendulum, more turns are generated. And as the length of the pendulum becomes shorter, the track on the axis becomes less obvious. And such observation can be seen in this chart. Okay, then let's move on to variation 2, the magnet number above the pendulum, which means the magnetic field I provide for the pendulum. And if there's just 1 magnet, and we can see that the track of it is still quite obvious on both x-axis and the y-axis. However, when it comes to the 2 and the 3 magnets, those are not the track is not so obvious as that of the 1 magnet. And then if I provide more about the magnetic field length, the x-axis is getting fewer and fewer, while the y-axis still moves on. And when it comes to 5 magnets, it becomes more obvious. So here's our observation. The number of magnets above the pendulum does not have an obvious impact on time, and the number of magnets above the pendulum does not have an obvious impact on the currents either. And with more magnets above the pendulum, it's less easy to move on the axis. According to the Lorentz force, we can say that as the magnetic field is larger, Lorentz force becomes more obvious, which can explain why as more magnets are above the pendulum, and the oscillation on the y-axis is more obvious. And here's our variation 3, which is the thickness of the table. And this variable is quite similar to the previous one. So this just proves that as the magnetic field is getting less and less, the x-axis will get less and less, and the y would still have some, but not so obvious. Which means that at this part, the force that influences most of it is the gravity. And as I get the table between them thicker, and both of them are less obvious to observe. And what is found? We can see that the thickness doesn't have the obvious effect on time. Both of them are about the same, and however, they are much shorter than the previous experiment, and with the table being thicker, more turns are generated, and the thickness of the table does not have a huge impact on the track of the pendulum. And as the magnetic field is less provided, it's more obvious to see the influence of the Lorentz force, which is linked to the track on the y-axis. And here's my conclusion. First, the swing of the magnetic pendulum is mainly influenced by friction, gravity, Lorentz force, and the magnetic force. And the Lorentz force is influence the movement on the y-axis, while the gravity and the magnetic force most influence the pendulum on the x-axis. And as larger magnetic force is provided, the influence of the magnet and the gravity will become less obvious. And that one is the Euler's pendulum eventually stops due to the friction. And this is the end of my report. Thank you.
So it's time to the question of the opponent to the reporter.
Okay, thanks for reporter's reports. Then here I have several questions that I'm going to ask the reporter about. The first is, please turn to page 3. That's, what kind of energy decay do you think it causes the energy decay of it? Just, do you see that there is swinging bigger and smaller and
Usually stop, yeah.
so what caused the energy decay?
I think the energy decay is mostly because of the friction between the surface of the table.
Friction, okay. And about the page 6, can you explain again what is the alpha and beta definition?
Oh, this is the alpha is the angle on the x-axis of the pendulum, and the beta is led on the y-axis. So, if they are all the same, then the picture, then their track should be quite close to this.
Okay, so about you have said you have magnetic couple. That's what kind of coupling it is? Is weak couple or strong couple?
You mean this?
In your experimentation, that's your couple mode. Is the weak or is strong couple?
I think it's a weak coupling.
Okay. And about the page 13, that I'm curious about why the motion of X and Y didn't seem like it's coupling. Like, because one is decreasing continuously and another
This
is.
is that's over later.
Okay. So it's time for preparation. time for the opponent to draw. Maximum time 4 minutes.
Okay, honorable jurors and fellow competitors, I'm your opponent from Team Scientist, Jinja High School, and today I'm going to oppose problem number 8, which is the Euler's pendulum, and about the problem statements that we need to discuss about the non-magnetic material of the plate, and we need to use the neon dynamic magnets, and we need to discuss and investigate about the highest edge release and study the motion, which is the magnetic rod, and about our main focus that we focus on how different pendulums works and how variation influences the movements of the pendulum. And here's the reporter structure, which he starts from the observation video, and he showed the similarity between Euler and the Wise pendulum. And in a theoretical model, he showed the friction and also the Lorentz force to explain the phenomenon, and his lack of setup showing, and in experimentation parts that he showed us a lot of graphs about magnetic pendulum, and in our conclusion, he concluded about the magnetic pendulum and thickness of effects, times, and turns. And here's the strong and weak points of the reporter, which the strong points will be they have good comparison in Euler's pendulum and also Y pendulum. And second, they have clear graph about the amplitude. And also the weak points will be they have lack of experimental setup picture. And the second is that they have lack of equation in the theory, which can describe the motion. And the third is they have lack of x and y axis in the graph. And the last is they have no three-dimensional experimental results, which we think is a little important in this phenomenon. And here are some points that I'll discuss later in the discussion, which first we will start with the observation of the coupling motion and also precession. And about the experimental setup, we have nothing to discuss. And the theory that they have, we might talk about the Lagrangian mechanism, which can lead to the equation of motion, and also the motion, about the precession, and also the frictions effects. And in the experimentation, we'll talk about the thickness of the table and the sliding motion of the magnetic rod. And let's move on to the discussion, which the reporter.
Okay, I can count.
That's the first problem about observation. That's about the coupling motion. You said is weak coupling, but as I see in the graph that your 11 magnets is, I think it looks like the strong coupling motion. Can you explain why?
Sorry, can you explain your question in other ways?
May I use the background?
Yes?
Thank you. So here, in the weak coupling motion will be like bigger and smaller, and here will be the bigger one, smaller one, and the strong coupling will be like the there's one, and it will be another amplitude peak. So
So the two peaks will
Now-
cover each one.
yeah, because you said there is coupling inside your experiment in the phenomenon. That's I think in previous graphs that it looks like a weak coupling, and in this graph it looks like a strong coupling. Can you explain the difference?
At this graph, the thing that most influence on the y-axis is gravity.
Yeah, right.
And if there is a more impact on the x-axis, then we should talk about. Then I should give it a larger magnetic field. So this can be at this part it can quite easily be seen.
So, okay, I understand your opinion, which in a conclusion is that when we use the gravitational as the most important factor in the experiments, which will lead to the strong coupling, and use magnetic field as the strong factor, it will be lead to the weak coupling motion. Yes. Okay. Since this problem is discussed, then let's move on to, do you think that, do you observe the phenomenon of a precession? Precession. Like there is two axes rotating, that there will be one axis about the object's rotation and the other object that the axis will rotate by this axis.
So I mean, have I observed three-dimensional?
Just two, yes, three-dimensional. Do you observe like some motions like this?
No, we just mainly discuss about from the bottom of the device.
Okay. Since that the opponent thinks that this motion is a precession motion, contains a precession motion, which the pendulum has a main rotation axis and the self-rotation axis, and it might be put in the observation. That's in my opinion. Okay.
I want to discuss it with one thing. Is that how to observe it in 3 dimensions? Observe it. If you just track a spot.
3 dimension, you can put a side view of a inclined angle of a side view, and also another view from the bottom, that you can observe multiple like angles and sides.
So I can put perhaps put the camera on different sides of the device to track if the same spots to see it moving track.
Yes.
Okay, thank you.
Okay, so the problem is discussed. Then let's move on to the theory. So since you don't have an equation of motion, that the opponent suggests that we could use the Lagrangian mechanism, which can lead to a equation of motion that can simply explain the phenomenon, which you consider the kinetic energy and the potential energy, and we can lead to a equation of motion that the opponent suggests that you can use in the further investigation, which we have some formulas about the Lagrangian mechanism, that you can do the analysis of the energy and from the energy part to do the investigation.
So
Yeah.
you mean I can see not just about the trend, but also but to see if it's roughly there and how much energy is losing,
Yes.
perhaps by friction or the gravity.
Yeah.
Okay.
And another question that I'm going to ask you about is that have you considered the situation that you give the pendulum a initial angular velocity? Like you give this pendulum a initial angular velocity, like it makes it rotate in, because you give it a
how to make it rotate? What do you mean rotate?
it will give it an initial force to the pendulum, not just fix it and release. It will give it an angular velocity.
No, in my experiment, I just simply put it down from 90 degrees from, yeah.
Okay. In our opinion, that we think this might lead to another interesting phenomenon that we can discuss about, is that in this situation, when we give the initial force to the pendulum, that in the xy direction, it will start off with a partial pendulum motion, and the motion might last longer than original one. Then maybe you can observe in the further investigation. And
So especially now, I can't, perhaps it's hard for us to make sure that the force even are the same.
you can use some force meters.
Okay.
Yeah. And about the friction of your theory parts that you haven't considered it a lot, that So I'm going to ask you about which friction do you think is included in the pendulum motion? Is the rolling friction, static friction, or the kinetic friction?
I think it is the static friction.
Okay, and could you explain why?
For that. And on this video we can see that that if we just say that from your point that this energy is decreasing.
Yes.
So and it just gets lower. So it doesn't have. I think it's just static friction.
Okay, so have you measured the center of mass movement by doing tracking or something to measure the center of mass movement?
No, I haven't.
Okay, so there maybe their center of mass may move for a little displacement, which the opponent thinks that might lead to the rolling friction, which will cause to the other explanation of the theory. Do you agree?
Yes. Yes.
Okay, so about our next question is that could you please yes turn to the experimental results that previous one. Yes. In this graph, that do you think there is? So you agree with there is a little rotation on the axis, right?
Yeah.
Okay. So this question is clear, and in the 15 magnets of your experimentation, could you please to print that? So what do you want to? So in this graph, that you just want to explain that the motion of this.
Okay. And as I just mentioned, that the two forces that influences are not the same. The XY axis. So there should be a certain frequency.
Okay. So
But at this part, since it's irregular, so the frequency is
understand that. Let's move on to the next question. Is that in the variable 3, that why do you think when the thicker plates, that the longer motion it will get?
At this part, I just want to prove that as the less magnetic force I gave it, so.
Okay. And in open view, we agree with the reporter, which when the magnetic force is smaller, that's the time that's longer. And since you use the desk to do your experiments, can you make sure that the experiments won't sliding? Like
I'm ensure that the magnetic are at the same place each time.
you ensure that you didn't track the center of mass, so maybe you can do
the upper one.
these sliding of the rod and.
Okay, thanks. So, opponent, you can summarize.
Okay, in the previous discussion about the motion test, we have discussed about how to the weak coupling and the strong coupling of the motion in the reporter's reports, and later on we discussed about how to use Lagrangian equation, maybe to lead to a equation of motion which can describe this motion. And next we discuss about how the friction will is in the phenomenon, and we think there's a rolling friction, and the reporter thinks it's a static friction, and also in that part we discuss about other experimental results. That here's all of my summary of the reports. Thank you.
Thank you. So it's time for review of these questions to both reporter and opponent. Please.
Thanks to the reporter and the opponent's presentation, there are some questions I want to ask reporter first. And in your experiments, have you considered the collision between the plane and the magnetic bar?
Well, since the surface of the magnetic bar attached, you mean on the pendulum?
Yeah.
Okay. And since the surface that which is attached to the table is not the same at each second, so we did not take it in consideration. But I still think that it should be a critical parameter.
Okay, thank you. And how about the opponent's opinion?
Comment about your question?
How about the collision between
The collision might cause the energy loss, and it might be one of the reasons of the energy decay. That's our opinion.
Okay, thank you. And here I would like to ask the reporter that how about changing the releasing velocity and how will the result change? The releasing velocity and
The releasing velocity. And at this experiment, we didn't do it. But I think we can. This is also something that worth to observe. Perhaps we will have different tracks.
Okay. And how about opponent's opinion?
Just like we just mentioned in the discussion, that if we change the initial angular velocity, that it might make the phenomenon last longer and make the time of the total phenomenon longer or shorter.
Okay, thank you. And I want to ask further, how does the magnetic force vary in the motion?
For magnetic force, it also provides the magnetic field for the Lorentz force, and it also makes the energy to decrease. Yeah.
Okay, how about opponent's opinion?
We agree with the reporter about the Lorentz force analysis on it.
Okay, and here's some question I would like to ask too. And you mean you change the number of the magnets, right?
Yeah.
But in my opinion, changing the number of the magnets also means that you change the mass of the magnets, right?
Right.
But here your variable is maybe the
Need to be more precise.
yeah. So but I think there are two variables of these experiments.
Yeah.
Okay. 2 minutes for preparation. check. Yeah, your computer, check the flow.
Okay. And I'm the reviewer from Team CYG. My name is Hui Chen, and today I'm going to review Euler's pendulum. And here's the problem statement. If you release magnetic rod and if you attach in the non-magnetic plane, and after you're releasing it, you should observe the motion of it. And here's the main focus of the reports. Here's the how different pendulum works, and the second is how different the rotation influence the movement of the pendulum. And here's the summary and comment of the reporter. And for theory, he compared it to the Y pendulum and Lorentz force and friction. And for experiments parameter, one is the magnet number, and another is the magnet number on the table, and the other is the thickness of the table. And for the conclusion, he mentioned that the friction, gravity, and Lorentz force and magnetic force influence the motion. And for comments for reports, as the advantage, I think he has a good time control and good amounts of charts and describe the phenomenon clearly. But for my suggestions, I suggest him to answer opponent's question more accurately, and he has a lack of the different view, and he has a lack of the parameter in his experiments, and didn't compare the experiment to the theory. And for my summary and comment of the opponents, and here's the comments of the opponents. For advantage, I think he has a well-prepared presentation and good time control. For suggestion, I think is too focused on theory parts and didn't explain his question clearly. And for the summary and comment of the discussion, and first question, opponent is, did you observe the phenomenon of precession? And reporter said no, well, we did not observe it. And in my opinion, reviewer thinks that opponent can explain the precision more clearly. And the next question, opponent asks, did you use the Lagrange to analyze the motion? And reporter said, did not do this. And reporter thinks that the reporter can explain more about the necessity of using Lagrange. And the next question, opponent asks, which friction is involved in the motion? Static friction, kinetic motion, or friction and or rotation friction? And reporter said, and reporter thinks it's just a static friction. And in reviewer's opinion, reporter thinks that there will be a lot of types of friction that is involved in the motion. And for my question, first is did the reporter consider the collision between the rod and the planes? The reporter said that did not consider it, and the opponent thinks it might cause the energy lost. And for my opinion, I think the reporter should consider it as a factor. And my next question, did you consider the change of the releasing velocity? And the reporter said it should be a critical parameter. And opponent said that change in the period of motion and agrees with the opponent. And the next question, how does the magnetic force vary? And the reporter said they have analyzed in Lagrange force and Lorentz force, and opponent agree with it. And my opinion is same as the opponent. And thank you for attention. That's all my presentation.
Okay, can you start? The last concluding remarks of the reporter, please.
Thanks for the opponent and the reviewer, and I have so much that you approve. At first, I can see my device in 3 dimensions, and which is more accurate to the problem statement. And I could consider it in the aspect of the energy. If I take consideration of the energy loss, then more parameters can be discovered, and the experiment will be more precise. And I should discuss more about the friction. The friction is a critical parameter in this experiment, but I haven't had enough investigation about this part, and for the variable one, the how many magnetic arm is a bit under the pendulum. There is too much variable in this I call variable, which is the mass and the length and the magnetic force. And the thickness of cable, this is not a serious. This is not quite a conscious parameter. Perhaps I should use more precise equipment to do the experiment in the future time. And that's it. Thank you for everyone.
Okay, so it's time for jury. Any questions? Please.
Okay. I want to ask some simple question. Maybe I did not quite catch your discussion. Is how many kind of torque in this problem? Because you see the rock, the swing, and the presets. Okay. So I want to ask. Okay, what's the torque makes it swing, or what's the torque makes it presets?
I think there should be 3 torque. I think there should be 3
Three
torque.
torque. Okay.
3 torque.
What is three?
And the one caused by the Lorentz force, and the one caused by gravity, and another one caused by magnetic force.
Okay, how about opponent?
I think there is also three torque, and one is caused by three torque on it, and there is one by the magnetic force and another by the friction that's contact between the magnet rod and might cause the rotation, and about the gravitational torque.
I think there are also three torque, and the first is the torque caused by the gravity, and the other is the magnetic force, and the other is the torque caused by the friction.
Other questions?
I think you abandoned the model, but then the two others pick it up. What is the Lorentz force in your model? I thought you abandoned it, you just skip it there, but then you bring it up again to answer the question. Can you say it again? What is the Lorentz force in your model? Oh.
And the magnet on the upper side, we can see that that will give it a magnetic field, and the pendulum we can consider as a electric field. So there should be a Lorentz force that will point to other tip.
You said the lower magnitude you consider as electric field?
Quite similar, but not the same.
How about the other two? Think.
We think in the opponent's view that we can apply the electric magnetic force on the just like Lorentz force on the model, but it's not one accurate about because it describes the electromagnetic. It's not only the magnetic motion. No. So.
Maybe I think the Lorentz force can describe a part of the phenomenon, but it should use another principle to explain the other motion. According to the Lorentz force, I think here he used it to describe why the rod is attracted by the magnet on the plane.
In your figure, there's a charge. So where is the charge in the experiment? What is the charge in the experiment? When you said Lorentz force, and there's the figure you said is the charge function affected by the E field. So what is the charge?
We did not draw it in our experiment.
What is the charge?
If the change of the magnetic force, and I think the charge will occur, but here he maybe use this charge to explain how the force to force the rods to release the gravity.
What is the charge?
Which I agree with the reviewer that when the magnetic force changes, the charge will happen. And can, yeah.
Can I ask one short question? Do you know how to calculate the torque for magnetic dipole in the magnetic field? Do you guys know? Anyone know this? The rod like a magnetic dipole in magnetic field. You can calculate the torque. Do you know how to do that?
If we use the calculation of magnetic dipole moment, that we might can.
No need to calculate magnetic dipole moment. Only it's less magnetic dipole, the rod like a magnetic dipole. Now you have a magnetic field. So you will feel some torque due to this effect. Do you know how to calculate this?
No, we don't.
What you told me? Did you?
Maybe I think in this model can calculate the accurate.
Just let me know you know or you don't know.
No, I'm not sure.
One more question. It's time for a break. Please wait. Okay, so the first is show the screen goal is following the formula 5, 6, 6, 5, and 5. The second component. Okay, sure. 7, 7, 4. 5 and 7. The last one for review. Okay, please show. 6, 6, 6, 5, and 7. Okay, please.
Can I think as a mu cross B moment cross magnetic field give you the torque. So I think you probably need to go a little deeper to understand what's going on in this model.
Yeah.
So I don't catch you to discuss this.
As you know more about this,
15分钟。
I don't have enough time for the theory.
Okay, so I announce that we take a break for 15 minutes. For the next speech.
This question is difficult to get view, the value of
Moment, the moment.
Yeah, but
You can, okay, the perception. you feel come the moment on the magnet, they have a magnet, so that's magnetic field. So now you got the
Why is that?
So
the magnetic.
this should be give you the
To the final round of this stage. So based on the rule, the first opponent has to challenge the reporter. Please.
So we would like to challenge number 13. Not available.
No, sir.
Oh, okay. We would like to challenge number 12.
12.
是一样的吗？就是，哦，sorry, but is it for?
Twelve is available. 12 is available.
No, but is this those like available for Jingchen? Or the last one? Or is that 品中?
是他们的题目。
Is this?
No? Okay, so there's a mistake. So what is the rubber available for reporting? Do we know?
我们偶破出15题，所以应该不会出现在上面。然后我们也偶破出15题，所以这个就是我们的可以接受的东西。那边是不是会不会是正确的？还是？
现在这边跟这边是一样吗？
那对，所以是
应该是正确的。
是那时候上面有15题有讲过了。
Opponent oppose 没有。
It's about is presented and rejected. Opponent doesn't come.
For example, we don't rejected problem number of
你说你们没有 reject
我
过？
们没有 reject 13题，或者是我们没有报告过，或者是我们过，但是那个已经被划掉，所以这明显不是我。
But the opponent has report problem number 13, so it has been lost.
Oh, say that again.
So I think in PF2, the opponent team have reported problem number 13, so is it shown on the screen that they can't challenge problem number 13?
So that's a mutual. There is
Is it because that the opponent team had report this?
So it's mutual that they reported number 13, so they don't change number 13.
Okay.
That's probably the.
Okay. So yeah, we would like to challenge number 12. Right schedule.
Okay, so reporter, several not. time is up. You should decide.
We reject.
Reject. Please choose
Okay.
another question again.
Available. We want to challenge number 11.
Okay.
We accept the challenge.
Okay, so the reporter accepts the problem. 11. So speaker, in each time, please write down the name on the report. Thanks. Okay. So I have to announce first, because at every stage, one person can speak 2 times. So please change the recorder. Only 2, our rules. So please change to another person, speaker. Okay, it's time. Before that, you can prepare for presentation.
Honorable juries and favorable competitors, I'm a reporter from King Scientist, King High School. Today I'm going to present problem 11 from failure rod. And we can see from this our statement, a failure rod is placed at the bottom end of the vertical tube. Apply the AC voltage of the frequency of the same order as the natural frequency of the rod to a 5-wire coil wrapped around its lower end. And when the ball is placed on the top of the rod, it will start to burn out. Explain and investigate the phenomena. And our main focus is study the resonance of the failure rod and estimate its properties, and investigation of the motion of the ball and the relevant parameters. And this is the process we are going to present today. Let's begin with the observation, let's do theory, and story is experimentation, and that's its conclusion part. And this is observation video. We can see the first ball starts to burn out after giving an initial disturbance. And this is like the initial height. We give it the initial height to it. And our available variable is the number of coils and the radius of the ball. And the ball, how could generate this bouncing? That's because the length low. And because the ball is magnetic, so the magnetic will revolution, and without initial disturbance, the ball will not bounce. And the third one is because with the too big magnetic field, the ball will not bounce. And this is a chart about the displacement of the. And this is a chart about the displacement to time. We can see this dot is about the gravity effect, and this dot is about the magnetic effect. And we define the dropping height and the frequency. We set the initial dropping height as 7 centimeters to control the energy of the ball, just like this picture. And we use the 330 kilohertz as the applied resonant frequency. And this comes to our theory part. And we want to explain the geomagnetic situation. And this is the failure rod. And when we apply it magnetic field, the dipole will change its directions. And these directions will make this geomagnetic situation, like this video. And
So we give it another direction of the magnetic field, and then the dipole will change its direction to the other way. And there's some definition about the Ferrier rod. This we call L, and the natural friction coefficient is this lambda equals to this friction. And about the resonance frequency, in this equation we can see that the calculation of the resonance frequency, and the low view means the permeability, and we can see this like C, we call it the speed of light, and the D is the length of the rod. And because it's hard to measure, so we didn't use it. And about the acceleration formula derivation, for this motion of the rod, we divide the motion as a simple harmonic motion plane, like this equation. And then the force analysis. The force analysis of the ball, we can see the gravity, the ball will suffer like the gravity, and then the force from length low will go outward, and the magnetic propulsion and the attraction will go to the downward. And this we don't have the formula to analyze it, so we will do it in our future work. It got too many conditions to calculate, so we didn't do it. And let's come to our experimentation. And we can see this our setup. We use some equipment like a function generator and a power amplifier and ruler and an archery tube coil and a Ferrier rod. And this is how we measure the COM. And we use the light. And COM means the coefficient of the magnetons, and the lambda can be expressed like 0.00139. And in our experiment 1, we change the diameters of the ball, and we control the initial drop height in the top of metal balls and the long of coils. And about independent variables, we find out the average bouncing height. And about the height analysis, we can see from this graph and the bouncing energy comparison with the different diameters of the balls. And this is a linear. And in the experiment 2, we change the numbers of the balls, and we also control initial drop height in the top of metal balls and the diameters of the coils. And we find out the average bouncing height. You can see from this graph, it also is a linear and a bouncing energy comparison with the different numbers of the coil. And let's come to our conclusion part. And before we talk about our conclusion, we will talk about some discussion. And the friction and the collision with the tube, it will generate the energy loss and stop bouncing. And this is our conclusion. The first one is about the motion of the ball is a kind of complex, and it's hard to calculate, so we didn't analyze it, just on our future work. And the second one is about the diameters of the metal ball increase, the average bouncing height will decrease. And while the numbers of coils increase, the average bouncing height will increase. And there will be some boundary conditions of the coil. And there are other relevant frequencies that may lead to other results. And this is our report. Thank you for your listening.
Great. Next time, so opponent give us questions.
Okay, so the first question I would like to ask, can you turn to the page that has the problem statement? Okay, so it is mentioned that you need to use the AC voltage, right?
Yes.
But what will happen if you change it to DC voltage?
DC, if we change to DC, the Ferrier rod will not change its dipole directions.
Okay, so it cannot be changed to DC, right?
Yes.
Okay, and also mentioned it needs to be wrapped around its lower end. So did you change it from the lower end to like another other part of the its rod?
We put the pole on the center of the rod. It will not jump.
Okay, so you did change the wrapped
The coil in the center.
yeah. So you did change the position,
Yes.
and it would not be successful
Yes.
in the experiment, right? Thanks. Can you briefly explain the motion of the bouncing rod?
Because the lens go and the magnetic repulsion cause this bounce it.
Okay, no verbal communication, you can write notes, but no verbal communication, okay?
Okay, so thanks a lot.
Okay, so configuration, right? Okay, opponent to the floor.
Okay, so I'm the opponent from Team CYJ. My name is Brian Hu, and the problem today I'm gonna oppose is problem number 12, rice kettlebell.
Sorry.
Problem number 11, balls on free draw. Okay, sorry for that mistake. A ferrite rod is placed at the bottom end of a vertical tube, applying an AC voltage of a frequency of the same order as the natural frequency of the rod. To find a fine wire coil wrapped around its lower end. When the ball is placed on the top of the rod, it will start to bounce. Explain and investigate this phenomenon. So the main focuses are: 1. Study the resonance of the ferrite rod and estimate its properties. 2. Investigate the motion of the ball and relevant parameters. So there is the summary and comment on the report. So the phenomenon he did explain the bouncing, and the theory part he uses resonant frequency, oscillation formula, and force analysis to explain the theory. And the experiment parts, there are 2 parameters. First, the diameter of the balls, and 2, the number of coils. And the conclusion are there will be some boundary conditions of the coil. And while the number of the coil rises, the average bouncing height is larger. And the advantages I want to give to the reporter are they are loud enough and have the presentation is well. And the suggestions I would like to have is they are lack of parameters and they should add more data or do more experiments. Yeah. So the discussion I want to have, we can separate it into 4 parts. So first observation, we can discuss about the motion, the bouncing. And second is the theory part. We can talk about the friction or the equation of motion. Third part is the experiment. So the setup and parameters it can be discussed. So the fourth part, conclusion, that the reporter mentioned that the boundary conditions and number of coils can influence the result, and we want to talk about that. So I would like to change it to the discussion. Thanks.
Okay, so you follow China.
Okay, so first question. So back to the question you haven't answered yet. So can you briefly explain the motion?
Motion. And because we give it the AC current, so the coil will make the magnetic field go up and work, and then by the magnetic static loads, it will generate the force by the dense load, and this dense load will make the ball go upward, and because the gravity, so the ball will go down, and because the ferrite rod has a magnetic friction force, so it put the balls go upward, and
So
it's called the bounce.
Bounce. And so it would go down because it's AC. But if it's DC, it would stays up, right? If I'm not wrong.
Oh, excuse me, okay.
I'm sorry, no verbal contact.
If we use DC, and then the ball will attach the ferrite rod.
Yeah. Okay, so yeah, so it's the same answer. You can't use DC, right? Yeah, DC voltage. Yeah. So the next question is that can you change the material of the wire, or did you try to change the material of the wire?
How do you want to change? Because we just use the coil to wire. You say wire or the coil or
like the material.
material of the ball or
Wire. Coil.
coil.
Did you change the coil?
When we change the coil, just change our magnetic field. It will don't have any influence about this motion.
Okay, so it wouldn't have any influence, right? So when it's bouncing, well, every time it falls down, stays at the same position. And can you show the actual video? So you can see that So I want to ask is that if every time the ball falls down, it would stay at the same position.
It will not.
Okay, so did you analyze it? Why it would not, or it would?
We just only analyze its frequency.
Okay, so so you didn't analyze it. But in your opinion, do you think that you can predict the falling position?
If you just like the chaos, it will not to maybe the same place.
So it would not stay in the same place, right?
Well, because our amplitude of the AC power supply is too high.
So sorry, the question I want to ask is that can you predict where it would land?
You can.
Oh, you can. So you think you can predict? Okay. So can you please turn to page 5? The parameter. Okay, so how does the radius of the ball would influence the whole experiment?
The radius of the ball influence the gravity force and just like its mass.
So
ball's mass.
So if the main change is the mass, wouldn't it be better if you write the mass of the ball?
But yes, it's right, and we will do it in our future work.
Okay. Yeah. So what do you think the if you change the radius of the ball, do you think that it can change? And what do you think it could change? Like the volume of the ball.
I think if we want to change the mass, we will don't use this variable.
No, I mean if you use this variable, what do you think it will change?
Because the mass change. And also
No, so let me rephrase the question. What do you think if the volume of a ball changed? What would it affect in this experiment? So I know you didn't change the volume, but I just want to have your opinion on.
The bouncing energy will change by
Okay.
these parameters and the magnetic reference.
Okay, so there is something it would be changed if you change the radius of the ball.
Yes.
Okay. Next, please turn to page 7. Yeah. So in this chart, can you explain why it would change to from this part change it to this part?
Because just like the free flow motion and it will affect by the gravity. So we can from the first part we can see it's affected by the most of the by the gravity, and then it will affect.
Okay, so why does the displacement have or the meter have the not the numbers are
just like when we check this video and we didn't have the just like our.
Also, you didn't put your
our rules at the wrong system, in a wrong position. Our rules.
Oh, okay, so you put the axis at the wrong position.
Our rules just like if the failure rod is on this way,
Okay.
and the pole must be here.
Oh,
Right. So when our rules is put here, and then the tracker will analyze this.
Okay.
This is a negative.
Okay. Oh, so the tracker will analyze that if it falls down, it will be negative.
Yes. So we to prove this.
Okay. So please turn to page 6. Okay. So I want to ask that how would it be a single harmonic motion? Because as you previously mentioned, you cannot predict where it would land, right? So why is it a simple harmonic motion? I think you would be right.
equals sine wave or sine recoil.
Okay. Okay, so just explain how does it change it to the simple harmonic motion. This is my question.
Because AC frequency will give me the equation of sine wave. AC.
Okay, so give it a sine wave, so it becomes a simple harmonic motion, right?
Yes.
Okay. Next part, please turn to page 21 and 22, or 21 and 22. Okay, so the diameter of the balls. So as we previously mentioned that if you change the diameter of the balls, then mass will change, right? Because you use the same material type of metal balls. So the opponent suggests that the reporter should only have one parameters at the same time. Do you agree?
Only one parameter.
Yeah, only one parameters at the same time.
Just like when we
Yes, no,
the
because
diameters is static and change our mass.
yeah. So if you because you use the same type of metal balls, so if you change the diameter of the balls, it will change the
mass.
yeah. So the opponent is trying to say is that you can he hopes that it should be only one parameter at the same time.
Okay, so
Yeah.
that's because we can find a different diameters.
And please turn to page 24. Can you explain how this graph is linear? Because
We didn't calculate in our theory, but when we do this graph, we find it is linear. So we have nothing to prove it
okay,
by
so
our experimental data.
so you didn't have enough theory to prove why it is linear, but the experiment shows that it is linear. Okay. Okay. Yeah, I get it. So yeah, I want to turn back to page 60. Okay, so can you briefly explain what this means? Because
that's the displacement of that's like the displacement coefficient.
how did you like put it into a theory? No, how did you put what experiment result would it prove? Like here, this one.
Just like our displacement to the time graph, and we S is like the height of the. It's the displacement of the rock, the rock.
Okay. So yeah, that's all.
Thank you.
Okay, so you can summarize.
Okay, so the summary of this discussion is that so the first I asked is if in the problem statement if the AC or DC would affect the final experiment. So yes, it would affect the actual result. And next I asked him did you try to put the coil on the different positions? And their answer are yes, they did. But if you put it on a different position, it would not be successful. And we did discuss about the chart, about the linear part. So they found it in the experiment that it's linear, but they don't have any theory to prove it. Also, they cannot express how the theory are put together with the experiment itself.
Okay,
thanks.
So now the reviewer have to question to reporter and opponent, please.
Okay, thanks for reporter and performance presentation. And I have some question I want to ask. Does the reporter know the load and current value?
Can you rephrase the question?
Is the current and the load.
Voltage.
Voltage.
Okay.
And how much is it?
We just use the volt to control our frequency. So
Okay, so you didn't
we did
change it?
control the volt, but only remember the frequency is the same.
Okay, so you didn't have to change it.
Just remain is the same value.
And if do you think that if you change it, it will make the experiment result changing?
Yes, but maybe it not work because we need its natural frequency, just like a natural frequency to make the experiment to.
Okay, and what is your?
So if you change the voltage, I think it will change the frequency, and it's one of the set they had the experiment setup they did mention. Yeah, so I think they mentioned that they are a machine to control.
Okay. And in your report, you had a chart that you say that is controlled with gravity and another thing. I forget what it is. Can you show it to me?
So the picture talking about gravity and magnetism.
Yes. And okay, so in here there's a gravity effect and there's a magnetic effect. And I want to ask is if you want, can you explain how the gravity effect in the after there is getting?
And that's because the gravity is very large number, so it will not show the magnetic effect. And maybe there are some magnetic effect in it, but it's too small. So we only can see the magnetic effect and the gravity effect in this.
Okay, so your meaning is gravity effect is lower than the magnetic effect.
In here is bigger. The gravity is bigger than the magnetic effect.
Okay, can you explain, can it is getting bigger and magnetic at the height?
We say here the magnetic gravity is bigger.
Can you get it right?
Okay, time. Start. Liberation time.
statement. A ferrite rod is placed at the bottom and end of the electrical to apply an act voltage of the frequency of the same order as the natural frequency of the rod through the fine wire coil while wrapping around its lower end. When the ball is placed on the top of the rod, it will start bounce, and I will explain and represent this phenomenon. So this is a reporter's performance summary, and their theory is clear explanation of the phenomenon, and their experiment is well connected to the problem, and their conclusion, their data is not shown to us, but their pros is a good use of their media, and there are clear explanation of their theory, but their cons as they didn't calculated a certain number of the formulae, and they didn't show the data of the experiment. And here it is opponent pros and cons. In their pros, their discussions with the reporter is their pros, and another is their good understanding at the problem. And their cons is they didn't discuss the distance between the magnet and the ball. And here is their discussion. Opponent asks, is the material of the line? And the reporter replies, it will not have any influence. And in our view, in reviewer's view, the discussion is with the reporter. And the second one is the opponent will ask, would the ball drop at the same spot at each time? And the reporter replied later as they just discussed the frequency. And in our opinion, it is something that should also be taken into consideration. So the reviewer thinks it should be analyzed. And the third one is the opponent asks the volume of the ball change. And the reporter reply is the bouncing frequency will change. And in our view, perhaps it will influence the result of the experiment, which needs to more theory and experiment to explain it. So there is a point there facing. The amount of the current might be also influence the results, and the distance between the ball and the magnet, and the area's content coefficient of the magnetic force and the gravity. Okay, and there's all things right now.
Okay. Finally, the reporter has to give the concluding remarks.
Here comes to our remarks. And the first one is about experimental. Experimental and you can see the first one is about we need to analyze more data, and it needs to be concluded. And then the second one is about we need to find a way to provide the data as a linear growth. And the third one is about we need to compare the data and with our theoretical value. And that's why it's about we need to analyze the error of this ball's motion in about theoretical. The first one, we need to find an explanation of the motion of the ball and give a clear formula to explain why this motion happened, and investigate the motion of the energy and the energy of the ball's analyzed. And this is our remarks. Thank you for the reviewer and the opponent. Thank you.
Okay. So it's time for question. Any question? Please.
Can one who show the statement of the problem? Problem statement. For the other one, show the problem statement. Okay, so in the problem statement, there are two places, the word place. Okay. So let me ask you two conditions. Which one is place? First, look at here. Which one is placed?
Can you rephrase?
Okay, so there are two placed in the statement, right? PLACED, right?
Yeah.
Okay, now let me show you two actions and tell me which one is placed. Placed. Is this one placed or
Oh, first
placed?
The second one is placed.
How about you?
I agree with the opponent.
The second one.
Okay. So then it looks to me the experiment is wrong. You dropped the ball.
You need to give me the force when we drop the ball. You will start to.
Now look at the statement.
Let's
Based on this statement, we can find the box. We need to give it the height of
Okay, second question. Can anyone explain what is the natural frequency of the rock? What is the natural frequency of the rock? Can anyone explain? Briefly.
And that is the range of the value that the rock resonates. The range of the value.
Okay, how about you?
Yeah.
Okay, I just agree with the report.
Okay. So, natural frequency is the frequency the rock will vibrate by itself. Has nothing to do with magnetics. Right? Okay.
So here is the natural frequency. Natural frequency means that something is oscillating. So do you think that in this question, what is oscillating? I think in your model, the length of the magnet is oscillating, or what do we think? What is oscillating in this question?
The rod is oscillating in this question.
The position of rod or the length of rod?
Can you say it again?
So the rod is oscillating, but the length of the rod or the position of the rod is oscillating.
The length of the rod.
The length of the rod, how do you think?
Yeah, but yeah, I think in this presentation, it shows that it should be that the length of the rod.
The length of the rod.
I guess it's
But did you estimate that if you want to cause a significant length change, how much magnetic field you should apply? Do you estimate this one?
We only calculate how many coils we need to use. And if you want to calculate the magnetic field, we need to use some coil and the magnetic field equation.
So the magnetic field caused by the coil can cause a significant length change for the magnet.
Okay, so is the jury talking about the boundary conditions?
Boundary condition. So why don't you think that the AC field will cause a magnetic field in the coil, right?
Yeah.
And the magnet will repel or attract to the magnetic field. Maybe the position of the magnet will oscillate, right?
Sorry, can you insist?
So you have magnetic field in the coil, right? And the magnet is in the coil, right? And this is the AC current.
Yeah.
So the pole of the magnet will the magnetic field will change.
Yeah.
And so you put a magnet in the coil. So the position of the magnet will also also change. You will repel or attract to the the magnet field.
Yes.
Right?
Yeah.
So then, I think it's not it's not the length of the magnet that change. Right? Because if it is caused by the length of the magnet, you should fix the magnet. Right?
And we fix the position of the rod, so that the length of the magnet will change.
Because I see your magnet is moving. So in your picture, in your video. The magnet.
Your magnet moved.
Yeah, your magnet move. You don't fix the. In your video.
This video is just the showcase of the turbulence. In the fact, it will become change the length. But just the video of the showcase about the magnetic static.
Magnetic static.
Okay. So please show your data. I think you make data. Not this one. Displacement.
Yeah.
Yes, this one. Because I think you make it wrong. Displacement is meter.
10 meters.
10 meters. It's curious. Very curious.
Yeah.
So you make wrong thing.
And the other one is 7 meters.
Centimeter. So
Centimeter. Okay, so no more questions. Okay, so now it's time for juries. Please wait. Okay, the first for the reporter is 4, 6, 4, 4, and 4. The second one is for the opponent. Please show. 6, 6, 4, 7, and 6. The final for the reviewer. Please show 5, 5, 4, 5, and 5. Okay, so thank you very much for attending this afternoon stage. So, 3 teams captain, please go here to check